computer. I'm going to go ahead and share my screen, and we're going to continue on with Chapter 13, Goal 3, which is reactions, and then we're going to continue on to Chapter 14, because those are the derivatives, and those are actually some of the also the reactions we have for carboxylic acids. All right, I just need to move this one over here real quick, expand it up. Okay, excellent. Okay, missing a couple people today, but we're down to 14, but hopefully they'll be able to see the video. Okay, so back to our reductions. Okay, the carbonyl group is itself very selective, where you can do it with palladium and hydrogen to reduce down your carbonyl, but that also reduces your alkene. We can use this hydride transfer agent, this sodium borohydride or lithium aluminum hydride, to reduce down ketones and aldehydes. However, we have to be very specific and have a very strong reducing agent to reduce down carboxylic acids. We have to use that lithium aluminum hydride. It's the only one that works, and it converts all carboxylic acids down to primary alcohols. Okay, so that being said, we have other reactions we can do. For example, if you wanted to keep your carboxylic acid and get rid of the alkene, you can do that catalytic hydrogenation that we learned to do in the alkene chapter, but it doesn't reduce down carboxylic acids. There's too many oxygens on that carbonyl, okay? So to do that, we can just reduce down our double bond by catalytic hydrogenation. Let's say in the second case here, we had a ketone and a carboxylic acid, and you only want to reduce one of them down. Your aldehydes and ketones reduce with the sodium borohydride, but your carboxylic acid doesn't. So you can selectively reduce one of your carbonyl compounds, and in this case, it's this one right here, to give us our primary alcohol, our secondary alcohol in this case, because it's a ketone, and our carboxylic acid is untouched. Now, if we wanted to actually do both of them, we could reduce it down to 2 alcohols if we used lithium aluminum hydride. Okay, that's how we would take it all the way down to 2 different alcohols right there. So we have selectivity. We can selectively reduce our alkene without touching our carboxylic acid. We can selectively reduce our aldehyde or ketone without touching our carboxylic acid. Or we can reduce them all down using lithium aluminum hydride. Okay, now let's go on to another reaction we have. So the first reaction we have is we want to take advantage of the fact that we have this alcohol group, and this OH group here, and we can remove that OH group and a hydrogen off of another compound here and basically lose water, that's where this comes from, and create a new functional group. This new functional group is a derivative of carboxylic acid. It's called an ester, okay? So we'll learn about naming esters in the next chapter, so don't worry about that just yet. But the idea here is that we're taking one electron-rich species off and adding a different electron-rich species to it. Notice there's still a carbonyl bonded to an oxygen, but this oxygen no longer has that hydrogen, so it's no longer an acid. We now have our new functional group, an ester. And so we call those, ester right here, is anything that's an R, carbonyl, O-R, okay? So the difference is this last R here. This last R makes it no longer an acid and turns it into an ester. Now, we typically do this in a reversible reaction where we use an acid. In fact, we do this in the lab for 2330 that we have, where we create a bunch of different esters that we use this sulfuric acid as our catalyst, and you heat it up in the presence of the carboxylic acid and the alcohol. And this generates the ester. And then it also generates some water, okay? Now notice this is an equilibrium reaction, which means if you took that reaction and added a whole bunch of water to it, it's going to shift the equilibrium back to the alcohol and the carboxylic acid. Okay, so this is typically a reaction where you can go back and forth. So if you have an ester, you can take it back to your carboxylic acid and alcohol. If you have an alcohol and carboxylic acid, you can take it to an ester. Now, to make sure that you get a high yield of the ester, you typically add a whole bunch of alcohol, or you remove the water as it's formed to drive the equilibrium to our products. Okay, so this is a cool reaction because you can either make the ester or break the ester using the exact same conditions. It's just whether or not you're adding water to the system. Okay, so, and the way this works is the idea that we have our carboxylic acid, it has a carbonyl, okay? That carbonyl still has that partially positive part on it. Even though we have this electronegative atom near it, we still have that partially positive carbon. And so we have reaction by a Lewis base that'll come in and form this intermediate here, okay? So now we have a carbon with 3 different oxygens bonded to it. Okay, it's not very stable, so what it does is it'll decompose. It'll either go back to the starting material by adding a proton, or we can add a proton to one of these OHs, and it'll leave as water, giving us our regenerating our carbonyl. And when we do it, the alcohol, the ether functionality in this case here, stays on there. That's why it's reversible. That's why it can go back and forth. That OH can come and kick out what it will become the alcohol, or it can go to the other side and become the ether. Okay, so we have a reaction that's completely reversible, and by having a whole bunch of this, you're driving it in this direction. But if you add a bunch of water, it goes in the opposite direction. Okay, so by removing water or having a whole bunch of alcohol, you're driving it to the products or the esters. All right, so now there's other ways we can have different functional groups with these carboxylic acids, okay? And all of these carboxylic acids have electronegative atoms, okay? So in the case of the carboxylic acid itself, you have OH. The oxygen is an electronegative atom. In this case here, we've switched out oxygen for chlorine, okay? Now, this makes it what we call an acid halide, or in this case, an acid chloride, okay? So we've taken off an OH and added this group here. So what this group does is that makes it even more reactive, because the leaving group in most cases is going to end up being a chloride ion or an acid, or like HCl when it leaves, okay? So this is our first functionalized group of a carboxylic acid. It's called an acid halide. A lot of times we'll just call them acid chlorides, because the chloride is the most common of this, okay? So we're going to use this right here in our derivatives chapter next, in chapter 14, to show you how to convert things from acids to acid chlorides and acid chlorides to other things. Okay, so, but first we need to figure out how to make the acid chloride. Okay, we've used this reagent before. We use this SOCl2 to make alcohols into halogens. Here we're use that same thing, and what's going to happen is we're going to convert this part of our carboxylic acid into the chloride. So it's a similar reaction where we're making this, we're reacting the sulfur with the OH, making it a good leaving group, and it leaves chloride behind. But in this case, it is now an acid chloride because it's bound to this carbonyl, and that makes it more reactive than your alkyl halide was, your alkyl chloride, okay? But we produce the same products of SO2 and HCl. So this is an easy reaction, usually takes a drop of base just to get it to go to completion. And this is not reversible, because when we drive it in this direction here, this comes off as a gas, this comes off a gas, and so it drives it to the product, unlike the ester reaction, which is reversible, okay? Now, once we make this, it's very reactive and can react with a number of different things. Okay, The next reaction we have is what we can call decarboxylation. What that means is we're going to lose CO2, okay? The reason it's possible is CO2 is a decent leaving group because it leaves as a gas. So even though it might not happen very quickly, notice the high temperature here, when it leaves, it doesn't go back. So it's not a reversible reaction, okay? So we can do this for almost any carboxylic acid. However, it makes it much easier if we have a carbonyl close by. And it has to be in a specific location. Notice this is what we call our beta-ketoacid, meaning we have a carbonyl that's not in the alpha position, which is 1 carbon over, but the beta position, which is 2 carbons over. When we have that species, what we can end up doing is making a 6-membered intermediate here that makes it easy to lose CO2, and we end up keeping the carbonyl or the keto group, but lose CO2. And the hydrogen that was on that carboxylic acid is being transferred to that alpha carbon. Okay, so this is what we call a beta keto acid, and it decarbonylates very easily with just a drop of acid. Okay, again, we can still do it because it's irreversible at high temperatures, but this makes it much easier. Okay, now here's why. Okay, remember the last chapter we talked about the enol-keto tautomerism, right? Here is a place where the enol-keto tautomerism plays a role, okay? So what we can do is, instead of having our carboxylic acid, let me pull this up and erase this stuff here. Instead of having it in this configuration where the OH is away from our ketone, we're going to rearrange it so that it's closer to that, okay? And when we do that, what we can have is this 6-membered transition state. And remember, that transition state just happens very rapidly, and all the bonds are moving at the same time in this one. And what happens when it does that is when these electrons come over here and these electrons reach out and grab the hydrogen, we end up with the enol right here. Plus, the only thing we have left here is these come down here, and since these have broken, we have a CO2. And the CO2 can go off as a gas, and therefore it's going to shift mostly, notice the arrow here, to the ketone. Because remember, the ketone is typically more stable than the enol, but the enol happens to be the first species we create during this, right after this transition state, and then it drives it to that product. And again, the CO2 goes away, so it is a irreversible reaction. We're going to product. Okay, so that's why it's so much easier to remove a CO2 from a beta keto acid, because you can form that intermediate, and that enol is part of that step. Okay, and that's the same slide. All right, so we're going to take that into our advantage and look at what our products will be if we did that here. So the first one I'm going to do is I'm going to do this top one here, and I'm going to redraw this slightly such to show you that, and so we're going to take this part out right here. Okay, so what I want to convince you first is that we have a beta keto acid. So this is our carboxylic acid right here. And so that makes this our alpha position, and this is our beta position, okay? So because we have that, we can now form that 6-membered transition state. So I'm going to redraw it again and draw our 6-membered transition state. And that one, and draw our OH with our carbonyl over here. Now, if we remember how the electrons go, we're going to go, the electrons are going to reach up and grab this one. These electrons are going to come down. These electrons are going to go here, which is going to give us our first product is our enol plus CO2, okay? But remember, our enol is not the final product because it's the least stable of the eno keto. So we have to redraw it as the keto, right there. So these electrons come in, this hydrogen goes over here when these electrons come out, giving us our keto species. So we go from this beta carbonyl carboxylate group. Okay. Alpha and beta is a designation for things that are the carbon next to a carboxylic acid. So if we named it IUPAC, we would name them 1, 2, and 3. However, because it's a common name, we don't name the carbonyl. The carbonyl is where we start our name. And so the one carbon over is the alpha carbon. The second carbon over is the beta carbon. And that would actually make this the gamma carbon, and this is the delta carbon, and this is the epsilon carbon, because it's further and further away. So the designation of alpha and beta has everything to do with being one carbon over from the carbonyl is alpha, and the second carbon over is beta. Okay, does that answer the question in the box? Okay, great. So that being said, we do have an alpha beta, a beta keto carboxylic acid, and therefore will decarbonylate very easily. Okay, now let's do the backwards of it. Okay, so we have a ketone now, but where was the carboxylic acid? So now we have to go backwards thinking, okay, well, let's first think about where that enol would be. And so if we were going to do the enol, well, there's no hydrogen here. So that means that when we had our enol, that the hydrogen didn't get transferred there. So we have to think it has to be somewhere else. So that means the hydrogen from the enol had to transfer to there, okay? If that's true, then we need to redraw this as the enol first to figure out where the next thing was. So if we redraw this as the enol, we're going to have this as our double bond and then our OH up here. And this is just our new single bond for our alcohol here. If that is true, that means our CO2 has to be attached to this bond somehow. This is where our CO2 had to be to form our 6-membered intermediate, right? Because we have, let's count them in green here. 1, 2, 3, 4, 5, 6 atoms in our transition state up here, right? So if that's true, that means our carbonyl had to be there. So let's try to redraw that without losing anything, okay? So let's start with the benzene ring since it didn't change, okay? And then let's put where the oxygen is there. And it had to be a ketone to start with, so we're gonna put that there. Now, the only bond that broke is this one right here between the CO2 and the carbon there. So I'm gonna put all the other bonds there. And now I'm gonna add the CO2, but instead of adding it as a CO2, I need to have it with a hydrogen on it, okay? So that means that had to be our starting material to when we made our product. So when we're going backwards from where was the carboxylic acid, the first thing we want to do is draw our enol form. And then you know where the double bond ends in that enol form, the other side where the OH is from where the OH is, that's where the CO2 had to be attached. Therefore, all the other bonds stay there. It's only this one bond right here that we have to break, and we have to make sure that bond shows up at the right place in the starting material, okay? So whenever doing something like this, you want to start with the enol form and know that your CO2 had to be attached to, let me do it in red so you can see it. That had to be attached to this end of the double bond in the enol because this turns into your ketone, okay? See how this right here gives you this, and now knowing where that enol goes, knows where your CO2 has to end up, okay? Okay, that is the last of our reactions with carboxylic acids. Okay, so we can selectively reduce down a carboxylic acid using lithium aluminum hydride to a primary alcohol. We can convert our carboxylic acid to an ester by using an acid catalyst and a lot of an alcohol and or remove water, okay? So this will create a different functional group, remove water and create our new ester functionality. We can use our thionyl chloride or SOCl2 to generate our acid chloride, convert our carboxylic acid to an acid chloride. And then we can decarbonylate these. We can remove CO2 and transfer that acidic hydrogen to the main chain, but it's a lot easier if we have a beta ketone, alpha, beta. If we have a beta ketone, because we form that 6-membered transition state, which gives us our enol. And that's how we can also figure out where we lost the CO2 if we go in reverse order. By knowing what the enol looked like, we know that we had to make our CO2 bond in that direction to go back to this system. So if we're trying to back up and figure out what we started with, we draw the enol form first. All right, that is our goal 3 for chapter 13. And while I'm transitioning over to our goal 1 for chapter 14, you can go ahead and put some questions in the text box if you need to. Okay, so the reason this actually goes in really well with what we just did is that 2 of the functional groups we're going to talk about in these functional derivatives of carboxylic acids have already been discussed. We're going to look at that ester, and we're going to look at that acid chloride. Those are 2 derivatives of carboxylic acids that show up in chapter 14. So they kind of go hand in hand. Okay, so the first thing I want to talk about is the nomenclature and properties of the different carboxylic acid derivatives. And then we'll look at some reactions, and then we'll figure out why some of the derivatives are more stable than others in goal 3. But we're only going to get through chapter 14, goal 1 today. Okay, so there are several different derivatives, and I've already introduced 2. I'm going to introduce 2 more on this slide, but they all actually look kind of the same, because in all of them, we're losing water, okay? So you can think, that's not necessarily how we make them, but that's how we can think about the derivatives, okay? So the derivatives I want to talk about are, number 1, the acid chloride, which we've already talked about, and we're going to talk about some more. The next thing is an acid anhydride, okay? In an acid anhydride, we actually take 2 carboxylic acid, lose 1 equivalent of water, and we end up with what we call an anhydride, which means without water. So if you can think about it, if you actually take an acid anhydride and add water to it, you get 2 carboxylic acids. Okay, so that's how we can think about how to name that. This one we've already talked about, the ester, and that's basically you take an alcohol and a carboxylic acid and lose water. And that's actually the mechanism we showed on how to do that. The last thing we have is what we call an amide, okay? And an amide is basically the nitrogen version of an ester. And so we are losing a hydrogen from the nitrogen and the OH from the carboxylic acid to lose water, and makes a nice new functional group. So let's look at all of these, right? We've replaced our OH with a chlorine, electronegative atom. We've replaced our OH with a carboxylic acid, still an electronegative atom. We've replaced our OH with an alcohol, still an electronegative atom. And we've replaced our OH with an amine, still an electronegative atom. So that's the great thing about carboxylic acid derivatives and why they're different than aldehydes and ketones. In an aldehyde and ketone, you have that carbonyl bond or that carbon-hydrogen bond, which is non-polar. All of these are polar bonds and therefore are much more reactive, okay? So keep that in mind. They're all electronegative atoms, and they're all more reactive than aldehydes and ketones. Okay, so let's talk a little bit more about that carboxylic acid chloride. Okay, so the idea with the acid chloride is you're basically removing water. So we go from an ic acid to an eel chloride. So you drop the ic acid. So you keep the O. Remember, you have the O from oic. You keep the O and you add YL. So it's oil. See, ethanoyl chloride. Sorry, I'm not trying to do a Jersey accent there, but it kind of fits. Ethanyl chloride. And when we do it with benzene or benzoic acid, we drop the ic and go oil. So it's benzoyl chloride, okay? So that's how we think about the naming of the structures. We're gonna lose water, we're gonna add a chloride. So we have eel chloride at the end. Ethanoyl chloride, benzoyl chloride, okay? So when we do an anhydride, we know we're going to have two carboxylic acids. If it's symmetrical, we just have to say what the one carboxylic acid was and add the word anhydride. For example, here, this was acetic acid and this was acetic acid. So that gives us acetic anhydride, okay? Now there are some, if you have a diacid and you can make a ring out of them, you can actually close that ring and that ring will create the species here. In this case, if we had the carboxylic acid on one side, it's called maleic acid. But when we lose water, the maleic acid turns into maleic anhydride. Okay, remember, all we're doing is losing water from two carboxylic acids. Okay, now, if you have two different groups, that's going to change things, okay? Because now you have an acetic acid and something else, so you have to name them both. And we typically do that in alphabetical order. So if this was acetic acid, that'll be first. This was benzoic acid, so we call it acetic benzoic anhydride. Notice we keep the ic and we just add, instead of acid, anhydride. So it's fairly easy to name. And then it's very specific about which groups you have. Okay. Now, this one is actually used in here, and these are called acid anhydrides that use phosphorus. The reason I mention these is they are actually used in the body extensively. They're part of your DNA. They're part of a lot of your regulators within your body here. We're not going to test on this, but I wanted to expose you to the idea that if you have two of them together, it's diphosphoric acid or diphos. If you have three of them, it's triphosphoric acid or triphos. So, now, let's go over and talk about esters, okay? So esters have a different way of naming it. We're going to take the ic acid off and use the term ATE, 8. Okay, so, but when we do that, we have to identify the carboxylic acid and the alcohol you made it from. So the way we identify the alcohol we made it from is we put that alcohol name first, and then we put the carboxylic acid name second with the ATE. So in the case of this compound right here, we had acetic acid as this half of it. So that's where that would be our acetate or acetic acid tate. And then we had ethanol as our other half of that's the alcohol we use to make it. So that's where the ethyl comes. So if you think about ethyl alcohol plus acetic acid, you get ethyl acetate, okay? So that would be the common name. But of course, acetic acid is actually ethanoic acid if we use an IUPAC name, but we still use the same thing where we have the alcohol we name it for first, and then the carboxylic acid second with our ATE functionality, okay? So alcohol always comes first, carboxylic acid always comes second with the 8 hooked up to it, okay? So that being said, if this was our carboxylic acid right here, we have 1, 2, 3, 4 carbons. So that's butane dioic acid, okay? But we made an ester out of it. And both of the esters, I'm gonna circle them in blue here, were ethanol before we did it. So that means we have diethyl as our front to show that that was the alcohol, and butane, dioic, but we're no longer dioic acid, so we're dioate. Dioate. So it's dioic acid, you drop the ic acid and add ate. Okay, now the common name is, let's see, oh my such. So this is succinic acid is our name, oh my such good apples. So the common name would be ethyl succinate. Succinic acid, drop the ic acid, add ate. All right, so that's our next group that we have. All right, if we take these and put them in a ring, that changes the naming system, okay? Just like whenever we have rings in other systems, we change the name in the esters as well. And the weird common name for the IUPAC name is called a lactone. So you can think about it as being an ester ring is lactone, okay? So in this case here, for the IUPAC name, we have to number from the carboxylic acid, carbonyl, and we have 1, 2, 3, 4 carbons before we get to the oxygen. So that's telling us we have a butane. So we have 4 carbons, butane, but now we're butolactone. And it's saying 4 because the oxygen is hooked to the 4 carbon. Okay. Now, however, in the common names, we have to go with the alpha, beta, gamma, but remember, alpha always starts 1 over from the carbonyl. So alpha is always 1 over from the carbonyl. Then we have beta and we have gamma, and that's where the oxygen's hooked up to. So this is called gamma lactone. Okay, we're going to use this same nomenclature when we name cyclic amides. Okay, so, but whenever you see alpha or beta, that's a common name, and it's always 1 over from the carbonyl. IUPAC names always start with the carbonyl of the carboxylic acid. Okay, so now let's go to the amides. And of course, nitrogen always complicates its naming because of how we say whether it's a secondary, a tertiary, or a primary amine. Remember, when we have a primary amine, that means you have 1 carbon hooked to it. When you have a secondary amine, it's 2 carbons hooked to it. When it's a tertiary amine, you have 3 carbons hooked to it. We use that same carbon numbering when we look at amides, but one of the groups is a carboxylic acid, okay? So in the case of our first one here, we have acetic acid right here, and we've reacted it with an amine, and therefore we have the acetic acid is acetamide, acet for acetic. You drop the ic acid and add the word amide. So there'd be acetamide, okay? Acetamide. And this is a primary amide because notice there is only 1 carbon hooked to this nitrogen and 2 hydrogens. So that makes it a primary amide. And an amide, of course, is the nitrogen bound to what used to be a carboxylic acid. Now, if there was already a group on your nitrogen here and you make your amide from it, it is now the secondary amide because you have 2 carbons hooked to it. And because that's a secondary amide, just like in the esters, you have to name what that group is. So in this case, we say that it's a methyl acetamide because it looks exactly like this, but it has a methyl group attached to the nitrogen. And we have to show them that it's attached to the nitrogen by saying it's an N-methyl. You're saying that methyl group's just not there. If it was methyl acetate, that would be an ester. N-methyl tells us the methyl group is on the nitrogen, okay? So that's N-methyl acetamide. Now, if we take that to the 3rd degree, or the tertiary amide, by adding another methyl group here, we now have N-N dimethyl, because we have 2 methyls on the nitrogen. Form amide in this case here, because we're using formic acid instead of acetic acid. And so we have M-N. N-N shows you that those 2 methyl groups are each on that same nitrogen, and dimethyl form amide. And this is a tertiary amide because there's 3 carbons bonded to that nitrogen. Okay, so that is, let's see, esters, anhydrides, acid chlorides, cyclic esters. Now we have amides. Now we need to do cyclic amides. When we have cyclic amides, instead of being a lactone like the cyclic esters, we now have what we call a lactam. If you think about it as tone is like a ketone, which has an oxygen on it. Tam is like an amine, AM for amine at the end. So the cyclic amides are also called lactams. Now, for IUPAC, of course, we do the total number of carbons to name the carboxylic acid, and then we have to show where the connection is. So in this case here with the IUPAC naming system, we always start with the carbonyl carbon. We have 1, 2, 3, 4 carbons in this carboxylic acid chain. However, the nitrogen is hooked onto the 3 carbon here. So now we have 3 butane. We drop the ic acid, so it's buto-lactam. Okay. Now let's do it again. Just the IUPAC name for the bigger one here. We have 1, 2, 3, 4, 5, 6 carbons in that carboxylic acid chain. Therefore, we have hexanoic acid. We drop the ic acid and add lactam, and we have 6 hexanolactam. Notice that's because the nitrogen is on the 6 carbon here. That's where the 6 comes from. This nitrogen's on the 3 carbon. That's where the 3 comes from. All right, so now I'm going to go to red here, and I am going to go to the common names real quick here. Again, we start 1 over from the carbonyl to start our alpha beta, which makes this beta lactam. Okay, that's the general species. There's not an actual common name for it, but the fact that it's hooked to the 2nd carbon over from the carbonyl makes it a beta lactam. In the case of the larger ring, we have alpha, beta, gamma, delta, epsilon. So that makes it epsilon lactam. It's hooked to the 6th carbon, or the 5th position over from the carbonyl. Okay, and we actually are going to use this in chapter 16 to make a polymer. Okay, so that is all of the different functional groups we're going to talk about. And the last thing I want to look at here is this interconversion. We're going to talk about this more later. However, I want to show you that all these functional groups can be interconverted if you use them correctly. The acid chloride here is the most reactive. That means you can make the anhydride, the ester, the amide, or the carboxylate salt from it. Okay? Once you get to the carboxylic acid anhydride, you can't go backwards. There's no going back. But you can make an ester, an amide, or a carboxylic acid salt from it. Okay? Once you get to the ester, right here, you can't go back. It doesn't go back, but you can make an amide or a carboxylic acid. Once you get to the amide here, you can't go make an ester from it. You have to go to the carboxylic acid salt. Once you get to that carboxylic acid salt, you can reacidify, and then you can either go back up and make the acid chloride, or you can make any of these from the carboxylic acid as well. So the key here is that our most electronegative atom, chlorine, is the most reactive. And then we can go down in functionality, but we cannot go back up. And we'll do an exercise on Thursday involving this interconversion of groups. Okay. Questions about that? Let's see, I have one last slide here. Okay, so this last slide here gives you some idea of what we can do with all the different carboxylic acid derivatives. Using that previous chart I showed you, I'm just going to kind of talk you through it here, is that we can start with our carboxylic acid and we can convert that to the acid chloride, or we can convert it to an ester, or we can reduce down that carboxylic acid to a primary alcohol. Okay, so that's kind of cool. Once we have this acid chloride here, we can actually react it with an alcohol also to make an ester. So we have 2 ways to make esters. We can go downhill from the acid chloride to that, or we can just go straight over from the carboxylic acid. The other thing we can do is we can react it directly with an amine, and that'll give us an amide, okay? Or we can actually, because this is more basic, we can actually go in that other direction as well. Notice we cannot do the back reaction. We cannot convert an amide back to the ester. It's a one-way street. Once we get to our ester here, we can also use lithium aluminum hydride, and it'll take it all the way down to that primary alcohol. It's going to reduce off that alcohol completely and give you your primary alcohol. What if you took your carboxylic acid amide and did the lithium aluminum hydride? Well, that's actually interesting because that'll reduce down the carbonyl only and yield you your primary amine. So that's kind of one of the really cool things about the acid chloride derivatives, is that you get to move them back and forth and back and forth and back and forth. And a lot of them go in only one direction, so that you can be very specific about going from functional group to functional group to functional group. For example, if we wanted to go a crazy route for this compound here, we can go to acid chloride, then convert it to the ester, then convert it to an amide, then convert it to an amine, just by going in that direction. Okay, so we're going to do a little bit more of that in the next two classes, and then also we're going to do a little bit of that on our in-class activity on Thursday. All right, is there any questions about that? We're right at the end of our time here, but we have time for a few questions.
You said you're gonna
Stop sharing so I can see your smiling faces.
Oh, you said you're gonna post chapter.
So I'm gonna go ahead and stop recording, and then we can start saving this when we leave here. I'm gonna stop recording.